Hi, my name's Omar Sheikh. I work as a structural engineer in California, one of the most seismically active regions on the planet. A lot of folks have been asking me my opinion on the recent Kahramanmaras Earthquake, which struck the Turkey-Syria region on February 6, 2023. To collect my thoughts fully, I wanted to make this video, so please join me today as we first talk about the basics of why earthquakes happen. Next, we'll take a look at the regional seismicity of the Turkey-Syria area. And finally, let's explore unique conditions which likely led to the scale of the tragedy which we all saw in the Kahramanmaras earthquake sequence.
Look at these flat sheets of ice floating on water. They bump into, scrape against, and pull away from one another as the movements of the water guide them along. When we think of the land beneath our feet, it may seem completely still, but it is surprisingly similar to our sheets of ice gliding over a surface of water. Let's remove the oceans from the surface of the Earth. What we are left with are the continents and giant tub-like basins where the oceans used to be. As you will notice, the entire surface of the Earth is just a rocky shell. The shell is not one whole piece, but is actually broken up into many separate pieces, like a jigsaw puzzle. We call this outer shell of the Earth the lithosphere. Let's analyze the individual pieces of the lithosphere a bit closer. If we flatten out the surface of the Earth onto a two-dimensional plane, as is shown here, we see that the lithosphere is broken up into 7 major tectonic plates: African, Eurasian, Indo-Australian, North American, Pacific, South American, and Antarctic. There are also many smaller plates, such as the Arabian Plate, but the 7 major plates comprise the bulk of Earth's surface area. So, how exactly are the tectonic plates similar to our sheets of ice floating over water? The answer lies in what is below the rocky lithosphere shell. The thin plates of the lithosphere sit on a soft and viscous layer of semi-molten rock called the asthenosphere. This is the same stuff we see spewed as lava from volcanoes. The convection currents within the asthenosphere and deeper layers are what move the tectonic plates of the lithosphere. So, to summarize, just as the sheets of ice are guided along by the currents of water, so too are the giant tectonic plates guided by the convection currents of the asthenosphere.
It's important to realize exactly how thin the lithosphere tectonic plates actually are when you compare them to the size of the Earth. Let's pretend that we took the entire planet Earth and shrunk it down to scale to the size of this globe, which I hold in my hand. This globe happens to be about 9 inches in diameter. If we were to peel off one of the plates, let's say the African plate, then the thickness of that plate with respect to this 9-inch globe would be only a few papers thick. Another point to consider is that the tectonic plates are moving slow, really slow. When we looked at our example of the ice rafts earlier on, they were moving a few inches per second, but that's because they're sitting on a fast-moving liquid, water. The tectonic plates, on the other hand, are sitting on a semi-molten and viscous layer of magma, the asthenosphere, so they're moving incredibly slowly. To put this into perspective, the rate at which most tectonic plates are moving is about 3 times slower than the rate at which our hair grows. The tectonic plates are rocky and brittle, just like a cracker, which is rigid and is prone to cracking suddenly when subject to shearing or bending forces.
In some cases, the tectonic plates are moving away from one another. In other cases, they are moving towards one another. And finally, along some edges, the plates are sliding past one another. For these crackers, my hands are what are moving them. For the gigantic tectonic plates of the lithosphere, what causes them to move is the vast amount of energy provided by the semi-molten asthenosphere, which they ride on. When the plates move past one another along edges, many times the jagged interfaces become locally jammed. As the larger plate continues to move, strain energy builds up in the locked zone until it exceeds the strength of the plate material, causing a sudden snap and local acceleration. For the gigantic tectonic plates, when such a snap occurs, a burst of energy is spread in all directions, like ripples in a pond.
We experience this burst of energy as an earthquake. This explanation of how earthquakes happen is referred to as the elastic rebound theory. This theory also helps explain why virtually all earthquakes which do occur happen at the boundaries or the edges of the plates.
The location within the Earth's crust where the primary rock fracture occurs to generate the earthquake is called the focus or hypocenter. The location vertically above the hypocenter at the surface is called the epicenter. The hypocenter typically occurs many miles deep into the Earth. Generally, given an earthquake of the same energy, it will cause less damage to the surface if deeper, and more damage to the surface if shallower. Turkey and Syria are at the junction of three large plates: the Arabian, African, and Eurasian plates. Turkey itself is mostly sitting on a minor plate referred to as the Anatolian plate. This smaller plate is sandwiched between the Eurasian plate at the north, the Arabian plate to the southeast, and the African plate to the southwest. The movement of the larger surrounding plates dictates the movement and seismicity of the Anatolian plate. The Arabian plate is moving northward and is exerting a northward force on the Anatolian plate. However, the Anatolian plate cannot move north because the gigantic Eurasian plate is pinning it from that side. The large African plate, on the other hand, is sliding under the Anatolian plate and is thus pulling on it with subduction forces. The combination of all these plate forces causes the Anatolian plate to slide towards the west and rotate counterclockwise. This unique movement of the Anatolian plate causes it to slip along its east edge, or the East Anatolian Fault Zone, and also slip along its north edge, or the North Anatolian Fault Zone. The major earthquakes which have occurred in Turkey have occurred along either the East or North Anatolian Fault Zones. These fault systems have predominantly horizontal or slip movements and produce shallow earthquakes which are particularly destructive at the ground surface. The tragic Kahramanmaras Earthquake, which struck on February 6, 2023, was along the East Anatolian Fault System.
To put the scale of the Kahramanmaras earthquake into perspective, let's take a look at a few infamous California earthquakes for comparison.
The Great 1906 San Francisco earthquake occurred on April 18, 1906. It had a magnitude of 7.9, over 3,000 fatalities, and aftershocks as high as 6.7 in magnitude. The Loma Prieta earthquake occurred on October 18, 1989. It had a magnitude of 6.9, 65 fatalities, and aftershocks as high as 5.2 in magnitude. The Northridge earthquake struck on January 17, 1994. It had a magnitude of 6.7, 60 fatalities, and aftershocks as high as 5.9 in magnitude. The Kahramanmaras Earthquake of February 6, 2023 had a magnitude of 7.8, more than 50,000 fatalities, and a powerful sequence of aftershocks with one as high as 7.5.
So why did the Kahramanmaras earthquake cause so much devastation? The answers will continue to unfold in the weeks, months, and years to come. However, based on my review of the data so far, I would like to offer the following reasons. First, the energy that was released in the Kahramanmaras earthquake sequence was extremely large. The East Anatolian fault system unleashed several earthquakes onto the Turkey-Syria region. The first, of course, was a magnitude 7.8 primary earthquake. Just 9 hours later, however, this same system delivered a magnitude 7.5 aftershock to the region. This is in addition to the hundreds of lesser magnitude aftershocks which also occurred. It's important to remember that after an earthquake, aftershocks are normal, as the tectonic plates which have just jostled past one another settle into a new position. However, aftershocks typically decay significantly with respect to the size and magnitude of the original shock. In fact, most aftershocks are expected to be at least 1 magnitude less than the original earthquake.
It is important to realize how big the difference is in just 1 magnitude. Let's say this yellow square contains all the energy of a magnitude 6 earthquake. The difference in seismic energy with just 1 magnitude is 32 times. So a magnitude 7 earthquake energy square would be this big compared to our magnitude 6 square. A magnitude 8 square would be this big. As you can see, it makes a big difference that most aftershocks tend to be at least 1 magnitude less than the original shock. Otherwise, a tremendous amount of energy is unleashed in a short period of time onto a region.
After an earthquake, there's a 95% chance that any aftershocks which occur within 1 week's time are going to be at least 1 magnitude less than the original shock. Sadly, that's not what happened in Kahramanmaras, in which the original 7.8 shock was followed just 9 hours later by a magnitude 7.5 shock. Even in a region in which buildings have been well designed for seismic forces, this level of seismic energy release would be expected to cause significant damage, if not collapse, of many buildings. Second, many buildings in the Turkey-Syria region were likely not designed, built, or modified per modern industry standard seismic engineering principles. The fact is that if buildings are built deficiently, either due to poor designs, poor construction, or both, then they're probably not going to perform very well during a seismic event. So if this information is known across the world, then why don't we identify buildings that we know to have seismic deficiencies and retrofit them and build all new buildings per code? The answer is that seismic design and construction generally costs more money. It yields a more expensive building, a more expensive project. So the onus is on the local governments to ensure that contractors and engineers who are within their regions are building properly. If the government is lax or if the government is corrupt, then a dangerous situation arises in which many buildings can be built in a region deficiently, causing a significant life safety risk to the citizens.
When structures are impacted by seismic energy, they move and oscillate. The structure must be designed and built rigidly enough so that it can properly absorb and dissipate seismic energy without suffering a collapse. During large earthquakes, buildings are expected to be damaged. The goal of modern seismic design, however, is that at the very least, the building will not collapse after an initial shock, so that occupants can get out. Proper seismic design requires special detailing of critical members of the building system. This usually results in a more expensive building to construct. If building designers do not follow modern seismic design principles, or if contractors do not build per adequately detailed plans, then the building could have serious structural deficiencies. For example, if insufficient strength or stiffness occurs at a lower level of a building, then the structure can have unacceptable movement during a strong seismic event, which increases the likelihood of collapse. This type of structural deficiency is referred to as a weak or soft story mechanism. Many modern seismic design building codes typically do not allow new buildings to be constructed this way, and mandate that existing structures with this deficiency be retrofitted. Simply put, critical seismic elements make the difference in whether or not a building will survive a large earthquake.
Though a complete forensic structural analysis would be needed prior to making any definitive conclusions, a number of widely distributed clips of building collapses in the Kahramanmaras earthquake appear to show what looks like a weak or soft bottom story mechanism.
In this first clip, which is reportedly in Malatya, Turkey, the bottom story of a damaged building appears to give out, leading to a collapse. As it appears, the top portion of the building is generally intact as the bottom story of the building gives way, causing it to lean to one side and fall on itself. In the second clip, we again see that the bottom story gives way first, and that the building above appears to be almost completely intact at that moment. The seemingly vertical collapse sequence continues floor by floor in the seconds ahead. In this final example clip, a structure damaged by the early earthquake sequence appears to suffer a bottom story failure along what looks like a storefront side. The bottom story appears to give way at the storefront edge, possibly causing it to lean towards that side and collapse. It is likely that the storefront side of the building had door and window openings, which may have made it laterally weaker or softer than the other sides of the building.
Finally, the East Anatolian fault system crosses a densely populated region. The fact is that if a lot of people or if a lot of infrastructure lie in the path of a potential earthquake, there's a high probability that there is going to be a large loss of life and significant economic destruction.
If we superimpose the East Anatolian fault zone onto a population density map, we see that large population densities are within miles of the system. In the city of Kahramanmaras, after which the February 6, 2023 earthquake was named, the 2021 population of the city was over 550,000. In Malatya, the metro population in 2021 was over 500,000. So, just in the cities of Kahramanmaras and Malatya, over 1 million people were exposed to the seismic risk of the East Anatolian fault zone.
Earthquakes are a part of the human experience. We all inhabit a world in which the ground beneath our feet is slowly shifting. For those of us who live on the boundaries of the gigantic tectonic plates, it's only a matter of time before the rocky interfaces deep within the Earth fracture to produce the next big earthquake. As we reflect on the tragedy in Kahramanmaras, hopefully we can learn, build better, and produce infrastructure which is more resilient against the natural hazards of our world. Thanks for watching this video. If you liked it or if you found it informative, then please make sure to like and subscribe.